Streamlining power consumption in data hubs of distributed clouds. Abstract, as per the growing demand for various new technologies, including Internet of Things and cloud computing, services end in an unparalleled strength intake for many infrastructures. Flexibility to scale, highly available and cost-effectiveness are concepts that can be understood using this framework of distributed clouds. However, the growth of these information facilities in cloud computing has resulted in uneconomic consumption of power. Infrastructures are over-provisioned in order to determine that the services are reliable, a memory so that data to be stored, computation and conditioning to cool hardware. Locus influence schedule algorithm to scale back cloud computation energy, also known as LACE, will reduce the consumption of the power used in cloud data hubs. This paper also describes an exhaustive study on the usage of IoT, which can be used to create a consumer-friendly power monitor and manage utility systems. The solutions for power efficiency and web awareness to allocate resources in cloud environments are described. Keywords: Internet of Things, data hubs, LACE, power consumption, energy efficiency. Introduction. Energy management is more important than ever in this digital age, which is important altogether depending on style of living and product categories. If it is household utilities or maybe the industry-related machinery, power must be optimized. The cloud assets has a group of interconnected as well as heterogeneous or homogeneous systems which have unproven assets like web, computation, and disk, etc. The most logic for their reputations include utilization, flexible to scale, high availability, tolerate the failure, reliable and economical, and straightforward to usage. Streamlining consumption of energy by cloud assets is among the significant topics survived in both in academia and industry. The main objective is to make the rule of implementing a self or auto-regulating electric meter, which will include analysis, management, and lift the use of facility and let the use of software application by user to access facility usage to track the service. The client should have control to access through the software application to utilities or computing services which will be connected to the server or cloud that might store required all the data associated with power usage, such as categorized by time, date, and utilities. The end client should also has control access and hold data to master computer, utilities, and application system through RFID and NFC. The connectivity fabric's role in power usage is also addressed. The era of computing and recent exponential enlargement of cloud services has concluded in energy consumption that is not cost-effective, which leads as danger to the atmosphere. E.g. of dangerous threat is generation of large carbon footprints of data hubs of cloud services. As per the resources, we can say that the typical or particular data hub consumes the maximum energy amount as equivalent to 25,000 households. A mean data hub has production quite 150 metric million plenty of carbon in a year. Fig 1 below depicts data hub of Amazon Web Service, AWS, located in Argentina, which shows various components such as systems for storage, switches, routers, firewalls, and controllers for application delivery. Thus, due to these many number of components, power consumed in these data hubs is large. Images. Fig.1 Cloud Data Hub of AWS in Argentina. 1. Emissions of carbon which are generated through computing of cloud are expected worldwide in 2021 of approximate total as metric million 670 tons. Also, the max use of power consumption at data hubs rise the cost of operation. In US in 2013, data hubs used and predicts kilowatt hours of 91 billion of power too. The massive volumes of power consumed at these data hubs increases operational costs. Green computation of cloud goal to save atmosphere from data hubs emissions of carbon by low consume of power. In IT industry, consumption of energy has never been a goal. 30 years back from 1980s, the sole goal has always been to produce more but also faster. Historically, this has been accomplished by cramming everything into a smaller package and operating processor at a better frequencies. Moreover, so as to make sure, infrastructures are over-provisioned in order to determine that the services are reliable. Thus, two metrics were developed as stated. Energy Facility Use Effective, EUE, and Information Hub Infrastructure Efficient, IHIE, in order to streamline power consumption. As a result, effective energy is among the most key measures in deciding running costs and total investments in contemporary cloud computing data hubs, as well as the industry's performance and footprint of carbon. Screenshot 389. Section I shows the introduction part. Section 2 contains the literature survey determining the streamlined power consumption in data hubs. Section 3 includes hardware and software optimization techniques. Section 4 explains the design methodology and different algorithms used to streamline power. Section V shows the results and Section 6 focuses on conclusion. 2 Literature Survey. Energies 13-01153G001. In 2018, cloud computing experts implemented the collective self-consumption as shown in Fig 2, which describes a smart meter which can be the combined form of an electric web with a fanatical infrastructures of control of ICT, which grants the previous to extend its flexible nature. Thus, the approaching huge-scale deploy nature of those smart meter has grant the development of latest techniques to manage energy, which will influence the extend the contribution of renewable sources within the mix of energy. 3. Fig.2 Improved photovoltaic self-consumption. The technique is also named as collective self-consumption, which is close to appear in many countries. This idea contains the grant to many consumers and energy sources, located during a low geographic place to determine purchase power to be used in that place. The cost required in data hubs of distributed clouds, which is covered by supported web-used tariff, includes both technological and non-technological semi-cost like energy loss within distributed generation, mainly wires and cords, for instance, due to its electrical resistivity. Aging ancillary appliances. Generator management solutions, like metering and so on. In 2018, cloud experts implemented the power-effective schedule framework by use of linear address theory. The study focuses on scheduling that saves energy, particularly for real-time tasks. 4. They suggested a linear address algorithm as depicted in Fig 3, to encourage the use of cloud assets, thus lowering the cloud system's energy consumption. Fig.3 A learning automata and its environment. The linear address thesis has been used to guess utilities use in order to prevent overuse/underuse of PMS, as well as shutting down idle PMS. They submitted a survey on resource allocation that is energy efficient. Cloud computation is a typical computer environment that stores data over the Internet. Their study examines the benefits and drawbacks of various allocation techniques, as well as issues which are open and directions in future in cloud utilities allotment. They also proposed a cloud-based scheduling architecture that uses the rolling horizon principle to schedule tasks in real time. An awareness in Power Scheduler will be intended to improve the job's schedulable and resource preservation. The cloud domain experts investigated multiple utility schedule schemes for cloud infrastructure as a utility. Also need to look at different scheduling schemes that support the issue at hand, as well as the metrics used for assessment. Researchers in cloud computing services domain implemented ARMA energy prediction model, which shows optimize web technology which are modeled to scale back consumed power by reducing web traffic in servers. 5. To prevent overlapping paths, the first method produces various disjoint spanning trees and chooses the reroute how path that uses the least amount of space as described in Fig 4. The second method moves virtual machines from server which are either under or overutilized by machine that is nearest to them in terms of network distance. The web simulation WS2 and the simulator Cloud Sim are used to analyze both methods. The algorithm aims to consolidate virtual machines on a limited number of computers by balanced consolidated assets, memories, processors, and communication bandwidth, accessed by adoption of cloud computation data centers at the same time. It takes into account a wide range of workloads and different resource consumption features. Because heterogeneous workloads have distinct utilization of resource features, goal is to lower the power spent by increasing assets utilization. The findings of the experiments demonstrate that multidimensional assets have a well-balanced utilization and save power when compared to other techniques. The algorithms, on the other hand, are completely centralized and include significant computing overheads. Also, the cloud domain experts and professors states that they have implemented IoT power control system by management of power and control appliances, which describes study on the IoT and how control power services has aided for the development of a more credible infra for energy optimization in home operations. 6. Further research into these area has resulted in the development of highly effective smart sensor systems, providing us the tools to make smart house utilities. As sustainable development initiatives are undertaken to implement a great home which is smart enough, also user compatibility and security take precedence over facility control. The poverty of electric and reuse energy assets in developed countries is limiting urbanization in these regions. Renewable energy sources are also commonly seen in some locations, but their optimization isn't satisfactory. 3. Hardware and software optimization. According to the report, pressing challenges in green cloud atmosphere is deciding the exact position of new virtual machine requests which came to servers in physical space in order to decrease energy consumption. This issue has spawned a slew of academic initiatives. However, such endeavors are still in their infancy and is divided in 3 different parts. Hardware, web, software optimized techniques initiation. By using flexibility in hardware which will governs computation of server capability by regulating running server frequency along with voltage, hardware optimization strategies decrease energy consumption levels. The DVFS method is described in the paper as a result of this method. DVFS makes use of a variety of the special CPU which will run in different levels of voltage as well as frequency. To reduce utilization of power altitude without breaking service level agreements endorsed load of work criteria on VM, DVFS chooses acceptable supply voltages and frequencies for processing components. They proposed the Power Awareness Utility Effective Workflow Scheduler, which also uses servers named as DVFS which will find the optimized frequency height suitable for task during a science workflow under deadline constraints, EARESD, 7. Under the deadline constraint, the optimized frequency for completing every task is found out by reducing the frequency of processor. Policies such as reuse of VM and ideal time reduction were commonly made into use to increase asset utilization effectiveness. But, since they require the use of specialized hardware, optimized hardware methods for clouds in green computation tends to be usually expensive, also will have limited scalability. 4. Design methodology and algorithms. Each of the 5 research papers had used different strategy and algorithm to make significant use of power and get the most out of cloud data resources. The experts of the respective research papers' real implementation and system design model is as follows. 1. Smart grids. 2. Learning automata. The energy used mostly by VM is categorized, active state energy consumption and idle state energy consumption. When a task is being executed, we suppose that the VM is active. The energy utilized in the idle state is similar to the energy consumption in the active state for 1 hour. The VM's processing energy is taken into account here as shown in scheduling architecture in Fig. 6. A VM's computation energy is the amount of energy used to perform the tasks that have been allocated to it. 9. 3. Automated power consume, appliance control. IoT experts proposed an approach that can be broadly categorized into 3 important parts as follows. 3.1 Sensor network. The design scheme offers a practical solution for regulating home appliances with the help of an AI modulator. This relies output of sensor to function. Sensor web use a combined form of LM35 temp sensors along with humid sensors joint via Zigbee for controlling house appliances if temp falls below a set point. 3.2 Smart meter. Untitled. Our smart meter is the most important component of our model. It's powered by a custom microcontroller that's linked to the facility's power sources. Renewable energy, power system, and finally auxiliary power are used to power the meter as shown in Fig. 8. The smart meter's main aim is the usage of renewable resource to the greatest extent possible before switching to grid power. 3.3 Cloud Server and Security. The implemented managing energy includes a knowledge managing system of server, just like every managing and optimized work or automatic system. However, in order to develop the effectiveness of IoT system, the design would include a cloud server rather than a central data center. 11. 4 Locust-inspired scheduling algorithm. A cloud infrastructure data hub mimics to a locust swarm in that both have huge no of server and a huge no of locust. A master is compared to the locust in this instance. A server accepts virtual machines from an arriving VM waiting queue while the locust eats grass, or poorer grasshoppers for an infant locust in the affable process, i.e. invoking of help server or the servers which are light. 4.1 Mapped Phase. The primary phase for all master types is mapped phase. A vivid master accepts an arriving virtual machine request during this phase, PS or WS. First come, first served, FCFS, is the method of allocating resources. As a result, the server which is first with good enough utilities receives the request and executes it. 4.2 Consolidation Phase. Consolidating virtual machines into a small number of PSs is the aim of the consolidation phase. VM will be moved from server which is light to assist server to do this. Hence, the VM consolidation phase can only be occupied by help servers. 4.3 Migration Phase. The request messages from the help master is received by LLS master during a migration phase, indicating the quantity of amount of availability of car. Then the LLS look for VM that will connect to an assistant master by the amount of earning of car. The moment LLS receives the required well-suited VM, it will send the most important to an assistant first master, then will continue till the moment when there will be no well-suited VM more. After migrating VM all of the available, an LLS will enter the idle state, and then mode of sleep to conserve power. The consolidation phase algorithm have a time complexity as O, M, when M is no of VM on a server. Fig 9 below shows the energy consumed comparison by number of servers in the particular information hub without and with optimization by LACE algorithm 12. Fig.9 Energy consumed in data center consisting of 1000 servers. 5 Energy prediction model using CloudSim and JMetal. Modeled a cloud-based data centers with multiple hosts, VMS with varying hardware and power-aware configurations using CloudSim library. The aim of the implementation was to optimize an influence-aware data center by varying decisions of VM allocation, selection algorithms, and hardware configurations. So as to seek out solutioning to the optimization problem, we used JMetal. Not only aim to undertake and find a solution to multi-objective optimization problem during this domain, but also tried to match the outcomes of those algorithm for the given problem. The consumption of energy and resources in big data centers is constantly increasing. Major challenges faced are in terms of energy and resource management, which affect computation, storage, and communication resources. Increased resource utilization allows for the reduction of energy demand. Typically, such large-scale data centers are focused on the following 4 goals. 1. Enhancement of energy efficiency. 2. Reduced execution time. 3. Maximum resource utilization. 4. Make task scheduling more efficient. V. Results. The energy prediction model as explained just above in section 4, subsection 5, is implemented using Java Spring Boot application to get optimized results. The results of energy prediction model without power optimization in Fig 10 and with power optimization in Fig 11, which are able to achieve above said 4 goals using CloudSim Simulator and JMetal, are as follows. 6. Conclusion. As per the findings and literature survey from above journal papers as well as the implementation of one of the algorithms, the following conclusions are drawn as follows. Found some interesting answers to the original issue, which was about power consumption in cloud computing data hubs. The best configuration for a cloud of this size indicates that a dual-core setup with around 30 hosts and 30 VMs provides the best energy use, which leads to streamline the power consumption in cloud data hubs. IQR, LR, allocation policies, and MC, selection policy, were found to be the most power-aware algorithmic policies. The data center was able to work with 6 to 7 kWh under these conditions, with SLA violations of less than 0.1%, ideal performance in 99.9%. This is great, and it demonstrates how power-aware systems can be used effectively across cloud infrastructures. With big configurations, however, the results may differ. In terms of enterprise cloud applications, the findings are minor but not negligible. Thus, there can be many algorithms such as self-consumption, LACE, renewable energy sources in green cloud computing, task scheduling algorithms, etc., which can streamline the power consumption, leading to efficient utilization of cloud computing data centers.